one of the things that you're going to learn about me, Victor, as I teach, especially as you learn more and more physics, I will try and give you what I call a trigger, or the first domino to fall in a chain, where you can say, oh, as soon as I see this, I know I'm in this branch of physics. As soon as I see this thing, I know I'm in this area of physics. I'm really big on trying to build circuits in your brain that kickstart you on the right direction, so that then you can take it the rest of the way yourself. And our trigger for today's lesson on relative speed is when there's more than one moving object. In fact, if you want to, you could underline that as being important. If there is more than one moving object, that's today's lesson. Relative speed, or what happens when there's more than one moving object. We're going to have to use our imagination a little bit. That's only temporary, Mesa. Don't panic. You just, I read that totally. Write the test, we'll talk. Okay. That's on YouTube too. Ready? Focus back. We're all good. I'd like you to imagine that you're in a car and you're driving and your speedometer is reading 100 kilometers per hour. A Ferrari goes past you. Its speedometer is reading 180 kilometers per hour. We're not going to convert these to meters per second because you're more familiar with car speeds in kilometers per hour. And there's also a tow truck parked at rest. If it's at rest, what's its velocity exactly as a number? Okay. What would the tow truck see? Then we're going to ask what you would see. Then we're going to ask what the Lamborghini would see. Well, first of all, the tow truck would see you relative to the tow truck. If the tow truck was sitting on the side of the road and looked in its rear view mirrors, first it would see your headlights getting closer in its rear view mirrors, and then zoom, and then it would see your taillights getting further and further away in the front. Does that make sense, Kayla? It would see you travel at 100 kilometers per hour. So the velocity of you relative to the tow truck is, I'm going to say, positive 100 kilometers per hour. Okay. You may notice that I've written you relative to the tow truck, Ferrari relative to the tow truck, Ferrari relative to you, tow truck relative to you. That's a lot of writing, so we're going to start to already abbreviate a little bit. Instead of writing Ferrari relative to the tow truck, I'm going to write that as V Ferrari arrow T. Our abbreviation for relative to, we're going to use an arrow, and then how about the first letter of the object, or something clever if it's object A and object B, or object 1 and object 2, however you decide to label things. Well, again, this isn't a big surprise. The tow truck would see the Ferrari go past at 180 kilometers per hour, and we'll call it positive because as far as the tow truck is concerned, the Ferrari is moving forwards. Why does the tow truck think the Ferrari is moving forwards? Because when it looks at its rear view mirror, it sees the headlights getting closer, and when it looks forwards, it sees the taillights getting further away. You got that? Now we're going to imagine what we see. First of all, what do we see for the Ferrari relative, I'll use Y for you. If you're driving along and the Ferrari is behind you and you look in the rear view mirror, what do you see? Are the headlights getting bigger coming towards you, or are the headlights getting smaller going away from you? So as far as you're concerned, you would interpret that as the Ferrari is gaining on me, it's getting closer to me, it's moving in a positive direction. But you don't see the Ferrari traveling 180 kilometers per hour. You don't see the Ferrari zoom. Why? Alex? So how fast do you see the Ferrari traveling relative to you? 80. Still moving fast, but not as thunderingly fast as the tow truck on the side of the road saw the Ferrari go zipping by at. By the way, what if the Ferrari was doing 100? how fast would you see the Ferrari traveling relative to you? Are you starting to see why we call this relativity, by the way? We're always going to be saying relative to what? How fast would the Ferrari be traveling relative to you if you're both traveling 100? What does that mean? Yeah, 0. Okay? The tow truck would see you both traveling at 100. The Ferrari would see you traveling at rest. You would see the Ferrari at rest. Now, what about the tow truck? How do you see the tow truck traveling? Well, when you're behind the tow truck, you see the tail lights coming towards you. Zoom. And then when you're past the tow truck, you see the headlights getting smaller and smaller and smaller. The velocity of the tow truck relative to you. Well, what's the difference in your speeds? 100. But I don't think it's positive. I think as far as you're concerned, you can imagine that you are at rest and the tow truck is in reversed at 100 kilometers per hour because you saw the taillights get closer to you, zoom, and then you saw the headlights retreat in the distance in your rearview mirror. Jaya, can you imagine that? As far as you're concerned, the tow truck is traveling backwards at 100 kilometers per hour. Now, we never say that because we always have a habit of measuring our velocities from the ground. But I'm telling you, mathematically, Victor, you can absolutely say your car is what's standing still and the road is what's spinning beneath you. Totally fair game. What does the Ferrari see? First of all, what's the velocity of you relative to the Ferrari? Well, it doesn't see you traveling at 100. How fast does the Ferrari see you traveling at? What's the difference in your speeds? Yep. Okay, why negative 80? Because as far as the Ferrari is concerned, it's at rest. It sees your taillights getting bigger and bigger as though you were backing up. We would say the Ferrari's catching up, but the Ferrari could say, no, I'm not going anywhere. You're coming towards me. And zoom, then it would see your headlights retreating in the distance. And what would the Ferrari see the tow truck traveling at relative to the Ferrari? Negative 180 kilometers per hour. You got to use your imagination, Odette, but does that make sense? Okay. Now, some of you right now are already saying to yourself, well, this is dumb. Of course, those are wrong. Albert Einstein came along and he asked, so which of those is correct? And the answer is they all are. Each one of those is mathematically perfectly valid. And from each one of those viewpoints, Kayla, you can construct a perfectly consistent set of physics rules. You can pretend if you're in the Ferrari that you're at rest and the earth is spinning underneath your wheels, and you will not arrive at any contradictions whatsoever with that. You can pretend if you're the tow truck that you're at rest and the cars are moving, and you will not arrive at any contradictions with that. You can pretend if you're in your vehicle that you're at rest and the earth is spinning underneath your wheels at 80 kilometers per hour and everything else is moving relative to you, and you will not arrive at any contradictions to that. I wrote, Mr. Dewick, is there a short way to write this? Yeah, I already showed you the arrows and things. So you don't see the Ferrari moving at 180, at 80. And if we want to add a direction, we can add a positive or negative. But typically, we're going to do relative velocity for a little bit, but then we're going to just chuck the negative and positive and say, all I care about is the difference in speed. The relative velocity of any moving object depends on your point of view, or the fancy word is frame of reference, reference frame. Sure, you see the car moving away at 80 kilometers per hour, but the other driver sees you moving backwards at 80 kilometers per hour. Oh, view details.
An Gleis 3 steht, aber alle überall.
right? Both of those are equally valid, and most of you probably assumed that it was the train that was moving to the right, not the station that was moving to the left, but I'm telling you, both of those are equally valid. You might have noticed this if you've ever walked on a moving walkway when in an airport. Some of those airports have those horizontal moving walkways, and you may have felt a little strange when you looked at the ground moving past you faster than your feet were moving. Okay, I see some of you nodding. Or you might have just stood still and seen the ground move past you, or maybe you walked backwards because, physics. Example 1 says this: what's the velocity of the train passenger relative to the observer on the ground in each case? So do we have more than one object moving? This is a job for relative velocity. How fast is the person walking? Can you read it? Let me zoom in for people at the back row. How fast is the person walking? 1.2. How fast is the train moving? So the person walking, as far as they're concerned, they see themselves moving forward at 1.2 meters per second inside the train. What does the observer on the ground see the person moving sideways at? 16.2. See it? So, velocity of the walker relative to the observer, 16.2 meters per second. We'll even add a direction to the right, or you could call it positive. What about here? What is the velocity of the walker relative to the observer here? Direction to the right. Now you understand, as far as the person on the ground is concerned, the walker is walking backwards because they see the walker pointing left but moving backwards. By the way, what does the walker see the observer traveling at in this first diagram? Sorry? Negative 16.2? Okay. What if the walker was running in this second diagram backwards at 15 meters per second and the train was moving forwards at 15 meters per second? What would the observer see the walker moving at? 0. Does that work in real life, Mr. Dewick?
I have a feeling that we are very close to a perfect demonstration.
So Mythbusters looked at this a few years ago. They asked, what if we were driving forwards at 60 miles an hour and we fired a soccer ball backwards at 60 miles an hour from a cannon? What should people on the ground see the soccer ball traveling at? Let's find out.
We're going to see that ball drop.
With the forward and backward momentum matched as close as they're going.
The backstory is it turned out to be far tougher to do than they realized. This took several days. In fact, it's near sunset, I think on their third day of trying to get this right. They're tired and a little spinny right now.
You get it. The pressure's on Grant for a perfect release.
I don't know about you guys, but that looked pretty good to me. Let's check the high speed.
It really looked good to the naked eye, but the judge in this case is the high speed.
Oh my God, it's like a cartoon. It's just in the air, it stops and it just falls.
Look at that. Fantastic. I mean, look, it doesn't move at all. It's going straight down.
Woo! We did it! We did it! Yeah! Vector edition!
So yeah. Okay. Example 2, we're going to do one more where we're concerned about direction, and then we're going to say who cares about negative and positive, Kayla. We just want to know the speed difference. We don't worry about which one's positive, which one's negative, because even those are arbitrary. You could decide the other direction was positive as far as you were concerned. A zebra is running away at 50 kilometers per hour from a cheetah going at 90 kilometers per hour. What velocity does the zebra see the cheetah having, and vice versa? So the zebra's point of view, the velocity of the cheetah relative to the zebra. Let's imagine the zebra has a rear view mirror. I know, use your imagination. It would see the front part of the cheetah getting closer and closer and closer and closer. Yes? So, as far as the zebra is concerned, the cheetah is running forwards because it sees the front part getting closer. How fast? I'll give you a hint. Not 50 and not 90. 40. What about the velocity of the zebra relative to the cheetah? Well, as far as the cheetah is concerned, it's not moving. But what it sees is the hindquarters of the cheetah, of the zebra, getting closer and closer and closer. It sees the hindquarters of the zebra slowly coming towards it. So as far as the cheetah is concerned, Odetta, the zebra is running backwards towards it because it sees the hindquarters getting closer, as though it was walking backwards. How fast? Yep. For the rest of the lesson, we're going to ignore the negative and the positive, and we're just going to care about the 40. So part C, I like part C, says this. Suppose the zebra starts out 90 meters ahead. How long will it take until the cheetah catches up? What's this question asking me to find? Sorry? Time. Now, here is something that you can make a mental note of. If you want to add this to your green sheet, you can. I'm going to say hold off on that, though, because I'll mention this on the test as well. For all relative velocity questions, if there are two objects moving at different speeds, you can assume that A is 0. I'm not going to give you also relative accelerations. In fact, that's a real problem. We're going to, for the rest of this unit, be able to look at objects that aren't accelerating. As soon as we try and have objects that do accelerate, Einstein said, ooh, everything gets really, really weird. So we're going to assume that A is 0, and V is 40 kilometers per hour. And instead of VI, I'm going to call it VREL, short for relative speed. What else did they give me? What's the distance, Quinn? If it had said 90 kilometers, we could actually just go with this as is because our units would all match. We wouldn't get an answer in meters and in seconds. We would get an answer in hours, but doable. We're going to have to convert, and I think I'm going to convert VREL to meters per second. How do I convert 40 kilometers per hour to meters per second? It's something to do with a 3.6, but I can't remember what. Does it divide by 3.6? Okay, so I'm going to make a little note here. VREL equals, my computer, they did a massive Windows update last week, and one of the consequences is my graphing calculator no longer works. I can't bring it up. I'm trying to find a workaround, but for now, I'm going to have to be a peon and use an actual real calculator. And so you won't see what I'm typing, but I'll tell you what I'm typing. Of course, you all have your calculators out by now and are following along, aren't you, Victor? Okay, here we go. So I'm going to go 40 divided by 3.6. Do you all have 11.11111 repeating on your calculator? Okay, so I'm looking for an equation that has an A, a V, a D, and a T in it. There is one, sort of. Which one? Sorry? It's D equals VIT plus a half AT squared. But what's A? So first of all, let's write it out. D equals VIT plus a half AT squared. What's A, everybody? So that means this whole thing vanishes. And if you're not accelerating, your initial velocity is your final velocity, is your middle velocity, is your, wait for it, relative velocity. I can modify this equation into D equals that. D equals VREL. A is 0. And okay, if your speed's not changing, then whatever speed you want to call it is that speed there. Eliana, what am I trying to get by itself? How would I get the t by itself? So it's going to be 90 divided by, I'm going to write 11.1, but I'm going to use my answer button, of course. In fact, if I do that, it works out to a nice, if I use my answer button, it actually works out to a nice decimal, not repeating. What do you get? 8.1 seconds. That right there is the great circle of life, Simba, the great circle of life. And what I mean by that is, if the zebra can get to safety in 8 seconds, zebra lives. If safety is 8.2 seconds away, cheetah eats. And you might laugh, you can turn the page if you want to, but look at all the math that we just did. It turns out animals do this instinctively all the time. Watch the nature videos and you'll see, oh, there's a herd of wildebeest, there's a herd of zebra, there's a herd of gazelles, and there's a predator, and the zebras or the wildebeest, they're chilling, they're relaxing. But they're watching and they're doing the mental calculations because they know how fast this animal can run. And as this animal is getting closer and closer and closer, they're watching. And then all of a sudden they all start to run at about the same time. They've done the math. Now is when we have to run if we want enough time to escape. But you don't want to run unnecessarily, because if you run unnecessarily, you're wasting energy. You're not going to pass your genes on to the next bloodline. So the evolutionary advantage here is the better you are at figuring this out, the more energy you'll save, the less you'll have to be grazing all the time, the less likely it is that you're going to starve during a food shortage when it's a drought or something like that. The better you are at this, the more likely it is that you'll pass your genes on to the next generation. So animals do this all the time. Example 3. Alex, is this an airplane question? You haven't read it yet. So, example 3, Alex, you might know the answer to this. If you do, shush. Nick and Cole are having an argument at an airport on a windy day. Nick says airplanes should take off in the same direction that the wind is blowing. That way the wind is pushing them from behind so the planes can travel faster on the runway. Cole says planes should take off into the wind. He's not really sure why, but it kind of makes sense to him. Who's correct? Alex, do you know? What's the correct answer? Why would you want to take off into the wind? Doesn't that slow you down? But it slows you down. How can you get more lift? Planes don't fly because of how fast they travel relative to the ground. Planes fly because of how fast they travel relative to the air. Air. Okay? Who is correct? Cole. In fact, it's possible to be traveling completely at rest relative to the ground and actually be flying relative to the air. Here is a pilot who made a very, very expensive mistake. This cost him tens of thousands of dollars. So the wind is blowing to the left of the screen. How fast is the plane traveling right now relative to the ground? Everybody? 0. Do you know how fast it's traveling through the air right now? Takeoff speed. Watch it. Wait for it. Wait for it. And here is the horribly expensive mistake that this pilot made. He should have anchored this plane to the ground with stakes. Because he did not, he's going to end up having to pay a pretty significant repair bill. And now you know why anytime we have wind coming, walk by Pitt Meadows Airport, those planes are staked to the ground or they're in a hangar. Okay? So what was the plane? What was the speed of the plane relative to the ground? 0 meters per second. What was the speed of the plane relative to the wind? Takeoff speed. So planes will always try and take off into the wind. That's why, by the way, every airport, every community airport, every major airport, they got those wind socks because the pilots are looking at those and they can tell which way the wind is blowing. You want to take off into the wind. There's actually more information than just that in the wind. Do you know how they're divided into knots? Ooh, okay, I'll have to tell you that later.
Yeah.
The where the windsock kinks down tells you how fast the speed is. Ah, boy. So for the rest of this lesson, we're not going to concern ourselves with velocity, with the negative and the positive. We're just going to concern ourselves with speed. We're specifically going to look at objects heading in the same direction or objects heading in opposite directions, either towards each other or away from each other. But the acceleration is always going to be equal to 0 if we have two moving objects. In other words, Victor, the equation that we're going to use here is going to be d equals v rel times t. No plus a half at squared. If you really feel like you want to add that to your green sheet, you can. Or if you realize that if a is 0, d equals vit plus a half at squared turns into that if we modify it, I'm fine with that too. Example 4 says, state the relative speed in each case. Let me zoom in. So in this first one, we have two trains going to the right at 40 kilometers per hour. What's the relative speed between these two trains relative to each other? 0. As far as they're concerned, both of them are at rest. What about these two trains? What's the relative speed between these two trains? 20? I don't care about negative or positive. Yes, the front train sees the back train gaining on it, and the back train sees the front train moving backwards as far as it's concerned, but who cares? We're just talking about relative speed right now. What's the relative speed here? Give you a hint. It's not 20. I'll give you another hint. Why are head-on collisions always so much worse than rear-ending collisions?
60.
Bear with me for a second here. I was like, oh, what's worse, a head-on collision or a rear-end collision? Okay, why? What's the relative speed here? 60. If they're heading towards each other, I think you add the speeds. If they're heading away from each other, bigger minus smaller. Sorry, if they're heading in the same direction, not away from each other. If they're heading in the same direction, bigger minus smaller. How many of you ever walked, sorry, first we're gonna do example 5. I like example 5, I like example 5, I like example 5. Example 5 is a nice question. Example 5 says, how long does it take these trains to completely pass each other? This would be a very, very difficult question, Kevin, if I tried to look at both of these trains as moving. But instead, I'm going to use relative speed. Dale, I'm going to pretend that this train or this train, I don't care which, is standing still. One of these trains is at rest. So I wrote here, since both trains are moving, this seems like a difficult task. The longer train will catch up and then pass the shorter train. But we don't know how far both of them will travel during this time. So here's the trigger. Hannah, are there two different objects traveling at different speeds? Say yes. This is a job for relative velocity. I'm going to use d equals v rel times t. Kevin, what's this question asking me to find? Example 5, when it says how long? Yep. So I'm going to go g equals question mark. What's a always when we have two objects moving at different speeds? I guess I need VREL. Victor, how fast is the big train? How fast is the left-hand train going? How fast is the other train going? Are they going in the same direction? What's the relative speed? 8. Victor, how could I use a 13 and a 5 and get 8 as an answer? Yep. Okay. What if they're heading towards each other? Are head-on collisions worse than being rear-ended? Add them. That's honestly how I still remember it to this day. Now, what's the distance? Look up. Here's my argument. For this back train to completely pass this front train, I think the back part of the train has to get all the way to there. I know they're both moving. I don't care. I'm pretending one of them is standing still. How far does the back end of the train have to travel to pass the front end of the other train? There are numbers in the picture that help you figure this out. D is 250. Kevin, get the T by itself, please. Dale, you with me? Okay, sit up. Kevin, how would I get the T by itself? By what? So T equals D over V. It's going to be 250 divided by 8. I checked my units were all nice. If not, I would have done a conversion. Okay, get your calculators out. 250 divided by 8. You get 31.3, 31.25. I'll go to 3 sig figs. 31.3 seconds. Is that right? So you can expect somewhere in your future a train catching up to another train. And as far as I'm concerned, oh, Kayla, how many different variables are there in this equation? As far as I'm concerned, I can give you any 2 and you can find the third one. I'm not going to teach you how to get the V by itself. I'll assume you can figure that out. I'm not going to teach you how to get the D by itself because it already is. Fair enough? Next page. How many of you ever walked on an airport walkway, the horizontal moving ones? Okay. Or they also have them in casinos and things as well, but probably if none of you have been in too many casinos because they'd kick you out. All right. As you hurry to catch your flight at the local airport, you encounter a moving walkway that is 85 meters long and has a speed of 2.2 meters per second relative to the ground. First of all, if it takes you 68 seconds to cover 85 meters when walking on the ground at constant speed, what's your walking speed? Okay. Maxine, what's part I asking me to find? I'll give you a hint. Not acceleration. What's it asking me to find? Give you another hint. Not time. What's it asking me to find? Loud. You need to say it louder. Speed and our symbol V, no vector. We're going to be in scalars now, okay? So V equals question mark. Ooh, Maxine, what does that phrase tell me? What's A? And the reason I had to include that is I don't yet have 2 different objects moving at different speeds, so we can't assume A is 0, so I included that in there. What's the 68? Good. What's the 85? Which equation? It's actually the same as the relative speed one, just no relative speed, right? A is 0. I think we're going to get D equals VIT plus a half AT. No A, so D equals VIT. Wait a minute. We're not accelerating, so VI is VF is that. Maxine, how would I get the V by itself? I have no idea what you're saying, but I think it was right, so say it louder. Yeah. Distance 85, time 68. What do you get? What's this person's, what's your walking speed? 1.25 units. That's about okay. Yeah, that's I'm walking kind of fast, but not crazy fast. That's airport walking speed because you're usually trying to get somewhere. Okay. How long will it take you to cover 85 meters on the walkway? So if you don't walk on the walkway, it takes you 68 seconds. What if you use the walkway? And let's assume that you walk on the walkway with 1.25 meters per second. Okay. First of all, Jay, what's part 2 asking me to find? Okay. What distance are we walking? Yep. Are there two objects moving, the person and the walkway? Sure, yes. A is 0, because we're not going to deal with an acceleration yet. I think what I need now is my relative speed. Have you been on one of those walkways before? Do they speed you up or slow you down using them? So what do you think this person's relative speed on, how fast was the walkway moving? I've scrolled down, but I told you somewhere at the beginning. How fast is the person walking? What do you think? Am I going to add them together or am I going to subtract them? Okay, the walkway speeds you up. So it's going to be, what was it, 2 point plus 1.25. I'll write that step just so that I'm looking at my notes later. I remember I added it. If in your homework you just did it on your calculator and wrote the answer and didn't show the plus thing, I'm okay with that. I can do that in my head, right? 3.45? Yes? Okay. Jay, what am I trying to find? Good. How? You even got the t by itself. I thought I was going to have to say to you, get the t by itself. No, yeah, let's get the t by itself. T is going to be d over VREL. It's going to be 85 over 3.45. What do you get? How long did it take me just walking on the ground? 68 seconds. How long did it take me here? That's why the airports put those in. Please don't think that the airports put those in because they think you're tired. Any of you that have traveled on airlines know they really don't care that much about your creature comforts. If they can cram more people in that plane, they're going to. If they could have you stand up side by side, they would. So why do they put those walkways in? It's not because they care about your fatigue. It's because that gets you to the next gate about 40 seconds faster. That means they can put through more planes in less time because airports lose money when planes are on the ground. They're making money when the planes are in the air. That's why they build those. Please don't think that they're building those because, oh, you're so tired getting off the plane. Again, I hope all of you have traveled enough on planes to know if you're not paying first class, they don't really care much about your comfort at all. Okay? How many of you been on the walkways before? How many of you walk backwards on them? So, okay, example B. Suppose on the walkway you turn around and you start walking backwards in the opposite direction just 'cause. What's your new speed relative to the ground? Well, is this going to speed you up or slow you down? So what am I going to do with the 2.2 and the 1.25? Which is what? I don't think so. I think 0.95, I think I'm doing it in my head. Is it 0.95? Is it 0.95 or am I wrong? Okay. Well, suppose you continue the entire length of the 85-meter walkway. Assume it's late at night and you're not ticking off other passengers. How long would it take you to cover? Okay. I guess, again, time is going to be distance over speed. It's going to be 85 divided by 0.95. And I get 89.5 seconds. Okay. Any of you been to Las Vegas before, for example? Have you noticed between many of the casinos there are moving walkways? Why is that? Again, it's not because Las Vegas cares about your comfort. It's because if you're not in the casinos, they're losing money. You don't They don't make any money when you're out on the sidewalk. Get them back into the building as fast as possible. I like example 4. I like example 4. I like example 4. Example 4 is a nice question. The police are in hot pursuit of a car which is 320 meters ahead and going 150 kilometers per hour. The police want to ram the car in 20 seconds. How fast do they need to go? Ooh. First of all, Nicole, what's this question asking me to find? Is there more than one object moving at different speeds? This is a job for relative speed. So the first thing I'm going to do is I'm going to say to myself, okay, D equals VREL times T. And I'm going to say, I think what I'm going to find is relative speed. We're going to pretend the bad guys are stopped at rest. What's the distance, Nicole? What's the time? This is going to give us an answer in meters per second, but that's okay. We can do a conversion. What are we asked to find? I think VREL. How would I get the V by itself? So it's going to be 320 divided by 20. 16, I think. Double check me. Yeah, 16 what, Luis? Units. That's how much faster than the bad guys the police have to go. Now, you might be tempted to say, don't write this down, V police is 150 plus 16. Why can't I add those two numbers together? Why can't I? Yeah? No, first of all, okay. Sorry, yeah? No, it's not. What's distance measured in? See it? What's time measured in? I gave it, right, seconds. This definitely is in meters per second. Okay? I looked at the units. But why can't I add these two together? What's the units for the 150? What's the units for the 16? I mean, Verizon might let you add them together, but we're not working for Verizon, right? You missed that video, you don't get that joke. So, what am I going to have to do with this before I start combining it? Convert it. I want to turn this into kilometers per hour. Something to do with a 3.6, but I can't remember what. Is it times? Okay, so 16 meters per second, how many kilometers per hour? 57.6? So, the police have to go that much faster than the bad guys. It's going to be the bad guys plus 57.6. I think I can do that in my head. 207.6 kilometers per hour. Okay? That's because the bad guys are going pretty fast. But another neat application of this, kind of in reverse, this is sort of how the police officer's radar gun is working. It's tagging your speed, it's tagging the police officer's speed, it's finding it's actually measuring the relative speed between the two of you, and it's using that to figure out how fast you're going. So it's actually getting this by itself. Okay. A little more complicated than that, but that's the gist of it. So what's the short version to calculate relative speed between two objects? If they're traveling in the same direction, bigger minus smaller. If they're traveling in opposite directions, toward each other or away from each other, bigger plus smaller, because head-on collisions are worse. A couple more short videos, and then I'll turn you loose on the homework. This one I'm going to mute because it's on a very, very windy day. Where is this, Mr. Dewick? So it's turn that off. This is a hang glider, a very nicely modified hang glider. You heard the wind very briefly. How fast is this hang glider traveling relative to the ground, Hannah? Pretty much zero, but how fast is this hang glider traveling through the air? Almost takeoff speed. In fact, the pilot is just waiting for the big gust. Wait for it. Is Video number 2 is terrifying. This motorcyclist owes their life to relative velocity. How fast is the motorcyclist traveling relative to the car? By an amazing coincidence, 0. If it was any faster or any slower, that motorcyclist is not around, because they would have gone either over the front of the car or they would have gone off the back of the car at speed. But by an incredible fluke, when they hit the car, they ended up at 0 relative to the car.
Бля, вот уроды, суки!
And then the last one. So I've jumped out of an airplane. Two others have jumped out of an airplane. I mentioned I jumped out of an airplane. When you free fall, you eventually hit terminal velocity. When you hit terminal velocity, you're no longer accelerating. You can also achieve terminal velocity on the ground, but instead of you moving through the air, you have the air move past you. We call this indoor skydiving. So you can achieve terminal velocity on the ground. This is pretty cool. Anybody done this before? This is on my list of things to try as well. So these people have practiced a great deal.
Spreading far, and I thought we remained free from its heart. You lit a fire out, and it's right in front of me. You lit a fire out, and it's right in front of me.
So how fast are they moving relative to us? 0. But how fast are they falling relative to the air? They're at terminal velocity because the air is moving up at free fall speed. And so they're no longer accelerating.
From afar, to a mindful, keep away all the words that ignite the flame. Our words will ignite the flame. You lit the fire out, and it's right in front of me. You lit the fire out, and it's right in front of me.
They really practice and rehearse. Okay. And again, the physics there is perfectly sound. It is perfectly valid to say that they're not moving and the air is moving past them. Or when I jump out of an airplane, it is perfectly valid to say that I was moving and the air was at rest. There is no right answer. Both of those are happening. It just depends on your frame of reference, your reference frame. What's your homework? You probably want to do these on a separate piece of paper. You can assume A is 0 for all of these. Number 1. Number 2. Skip 3. 4 is good. 5 is good. 6 is good. 7 is good. 8 is good. 9 is good. You may have just noticed I gave you 1, 2, 3, 4 police car questions. That's probably a hint that I like this question. I like this question. I like this question. Oh, another train question. Number 10, number 11, number 12. Okay? You got 15 minutes. You can probably get almost all of it done in class, and I will happily help you if you have any questions.